All right, so basically, I'm Vijay Gill, and this is Chris Wright. Chris Wright is actually one of the engineers who works in the same group as I do, and we are responsible for media access and caching part of the network, and I'll explain some of the other parts of the networks as we get to them. So when I started working for AOL, my mom asked and called me up from India and said, hey, I heard you're working for AOL now. What are you doing there? So I was like, hey mom, you know when you log on to AOL and you have mail and the voice says, you've got mail? Well, guess what? There's a warehouse filled with thousands of people and I'm one of them, and if you have mail, I speak into this little microphone, you've got mail. So it's been 2 years and my mom is still trying to log on to it and check her email and hoping to hear my voice. So I think at this point I should probably tell her that that's not going to happen. It's a pre-recorded voice, but we'll let it go for now. So we're going to look at the problem space, what we are trying to solve here, because although some of the stuff we do is cool, nobody's really paying us, especially in this environment post-crash, to play with cool stuff. We actually have business problems to solve, and we're looking at them. And AOL has a huge set of networks. We will only focus on streaming and caching portions of that network because, well, that's what we are, our main focus is on. And we will go over the caching and the streaming, not in that order. So this is what the kind of the internet looks like, right? You have the internets, you have the backbone routers, you have things that connect to data centers. So this is how the thing goes. Do we have a laser pointer, Susan? And this time I promise not to shoot myself in my own eye with my own laser pointer. But so this is the context in which we have engineered and built our data centers. So this is the spatial view of the network. And while you can see the scope and size of the network, it's not as interesting as this view, which is actually a utilization and time view of the network. This is far more interesting from an engineering perspective. This is far more interesting from a requirements perspective because you can see if you overlay the census data from last year onto this map, you will see that the vast majority of the user base, so to speak, is either on the California side, the left coast, or the right coast for the US, and of course certain major cities in Europe. So you overlay your spatial build out where to match the population centers. So this is a spatial view. Laser pointer, someone? Anybody? Anyone else? Avi, with your 20 milliwatt? Any idea? Loud. So, if you look at the spatial, at the utilization and the time view of the network, this is from a tool that is built by some of our internal tool development people. They map various bandwidth utilizations from the network onto this graph. So if you look at the network, you will see the red dots and the pinkish lines. Those represent high bandwidth points in the network or high bandwidth links in the network. So the problem we are trying to solve is to give the best user experience possible with the minimum cost of maintaining that service, because that's the only way you can survive. You have to have the best experience at the minimum cost. So if you look at the bandwidth, we will look at the bandwidth as a proxy for cost, because if you run out of bandwidth, you have to incrementally add more circuits and they cost money. And if you look at the latencies, and I'm only showing a few of them because the rest are relevant, you get the idea. You are looking at latency as a proxy for the user experience. People normally go online and expect it to be fast, and for some definition of fast, in the many definitions. And that can, for the first order, can be approximated by the RTT, the latency, and the jitter. So this diagram here sets out our problem space. We want to minimize our cost and provide the best user experience within those parameters. Of course, in '99, we just had to provide the best user experience without regard to cost. Unfortunately, those days are long gone. So Then we look at our major peering points, and those peering points normally jump out as things that you want to push content to. Because what we're looking at here is something that people like FedEx, Walmart, Amazon.com have been doing for years. Basically, what you're looking at is a large operations research problem in optimizing your cost of goods distributed. And in this case, we are not pushing parcels, or we are not shipping parcels, we are not moving goods around internally, we are just pushing packets. But the same equations, the same operations research principles can be applied to the network. So if you look at the network, you will see certain, and this is a very small multivariable problem. We have been doing it intuitively in some cases. I mean, this is actually a fairly small network if you look at it. In number of like the variables we have to optimize for. So most of the stuff we can do intuitively, like this looks like a good place, and we'll get approximately close to the correct answer. And sometimes we apply a little more research into it, and we optimize the network based on that. So basically, the solution, given the solution space, now we have an answer. What we want to do is we want to distribute the thing that costs us money, which is bits, as close to the user as possible. This optimizes two things. This reduces our overall bits carried on the network, reducing cost, and improves the user experience, leading to a better service. Hey, Susan. I'm going to point it away from me because I want to get shot. This one's better. Whoever it is, like, catch me afterwards. I'll probably walk off with it. So what we're trying to do is we're trying to distribute the right content to the right place. Basically, try to take the content from our data centers and push it out as close to the user as possible, using various techniques such as content distribution networks, distributed IPTs, and distributed caches, because cache is content. Web pages are content. And things like we've developed in-house, like the UltraVox. And we'll go more into detail later. And of course, obviously, the best place to put content, cache it, is on the user's PC directly, because, well, your RTT is almost zero. And so there are things like AOL Top Speed, which is one of the products we sell, which actually reside and do a much better caching job on the user's PC than, say, the default program given to us by Bill. So having said that, this is what a functional breakdown of an AOL data center looks like. Keep in mind, this is not necessarily the topologically correct view. This is basically functional. I will be focusing on the two red circles here, which is basically streaming networks and the web cache networks. Each one of these little silos here could take up an entire presentation of like an hour. What is extremely interesting, and which unfortunately I don't have time to go into today, is the Oscar-Boss complex. The Oscar-Boss complex supports AIM. And the amount of engineering and packets per second flying around inside Oscar is actually stupendous. Unfortunately, we will not be able to get to those. So basically, data center design philosophy. The entire data center is in-sourced, so to speak. Chris, myself, James, I know he's walking around here somewhere. This group, Watson, we all engineered this. This is engineered within our John Chance's organization, who was our SVP, I believe. And it's designed, implemented, and operated in-house. There's no external organization that touches this. So we own it end-to-end, which has some optimizations, because now we can make sure that the thing is done right. It has some problems in that if stuff breaks, we are responsible for it. Ideally, we want the responsibility without any blame, but can't have it all. So basically, the network it looks like a fractal, if you would. Every component inside, we try to like dual home, have two of each. And then the paths, we have redundant paths. And then at the top level, we have redundant data center. So we can lose any cluster and migrate the users either transparently, for example, with Oscar or Boss, or redirecting in DNS routers for other stuff into something that is still up. We're also not a big fan of VLANs. We're not a big fan of VTP. We're not a big fan of layer 2 networks in general. They tend to cause more problems than they solve in our experience. So we basically try to stick to layer 3 and above as much as possible. Is Richard Colella in here? Oh, If he was, you would have asked him about some of the ATM bridging stuff. And eventually, we come to system review. This is a very important part of AOL. We go through the backbone, we go through data centers, and we review our current bandwidth utilizations, our current member counts, and see what would happen if X components failed. We just normally look at the components and we just take a bunch of clusters out and see if we can map the remaining capacity we have available onto the demand. So this is what the data center clusters in Northern Virginia look like. There is a reason you can't put them up here. There's nothing visible, because to actually really see them, you would need a plotter sheet about the size of this table, wide and about this long, so you can read what's on the things. So this is the context of the AOL data center. And if you take the data center cluster out, we will only focus on the cache part, which is this like block box over there, and the streaming networks. Some of the networks down below represent the Oscar complexes, which gives you some idea of what the network looks like. So caching. So when AOL was started out, the users were terminated on these complexes, like the dot complex, the pods, and each one of these systems was designed to support X number of users. And of course, X changed as the capacity of the system increased, as we got better CPU, more horsepower in the boxes. The problem with this architecture was that it was fixed. So each switch, each cluster supported a fixed number of users, and the problem with that was you couldn't scale systems that were running out of capacity. Now, of course, the simple answer is, why don't we throw out some of the, say for example, we ran out of DNS. Why don't we throw out the DNS switch boxes and replace them with faster CPU, which is normally the approach you would look at from a theoretical perspective. Unfortunately, our financial planning people would shoot us if we try to do that, because we have lease cycles, we have amortization schedules that we have to adhere to. So we just couldn't, for example, throw out a couple of boxes and replace them with faster boxes. So basically, whenever we had to build more capacity, we had to build a node. So we built on the unit of maintenance, the unit of construction to support a user was a node. And so we had to build that node out. And so the solution was decouple each service from the fixed nodal architecture into a farm, so to speak, where you farm out different services, for example, DNS farms, caching farms, and as each cluster of each particular service ran out of capacity, you would just add more hosts there. Much easier to do than trying to swap in-flight machines that were on lease return. So basically, we decoupled service growth from our nodal architecture. So this is the farm design. So you have the farm, you have the web cache routers up top, and each of these little boxes, now silos, provide a service, and you can basically arbitrarily scale each one of these in any dimension that you need in terms of CPU, memory, or space. And I'll go more into detail in a second here. So this is what the new web cache architecture looks like. Keep in mind that this is like a dot on the big green map that I showed earlier. So you have the IPT farms, which are the tunnels, which terminate the AOL user, the tunnel users, that is, and you have a whole bunch of them. I have removed significant amounts of information from the slide in interests of visibility, so to speak. But there's a whole cluster of these. The AOL user comes in, terminates on one of these farms, and then they do, these clusters provide the various services that we need. And I think we have some of the IA people here who actually run the hosts over here, and that they do the scaling stuff. So all in all, this cluster here serves about 13 billion requests a day, which is a fairly decent amount of requests to do, I would say. And hanging over here is the UltraVox, which is 8 by gigi. Each one of these links is 4 by gigs. And we'll go into the UltraVox in the streaming part. So taking an example of how, and in interest of time, I'm only going to go into the DNS part of the design. So this picture ripped wholesale from the IA web page is actually here. So the user comes in, he makes a request to the IPT farm switches, which are those switches here, these. And the farm switches then load balance. There's a virtual DNS server address sitting at a layer 4 on the farm switches. You send a request to the farm switches, and there's of course things like layer 4 NATing in reverse and forward direction happening, but I'm just not going to go into them because I don't want people's head to explode. So you make a request to the DNS farm switches. The DNS farm switches will load balance the request using a round robin predictor onto the barn switches. There are 2 barn switches as we've seen here, barn A, barn B. And the barn A and barn B switches then do a new foundry technique called stateless load balancing. And they will spray that request, regardless of source and destination IP, across the farm of DNS servers. And we've been trying this out, and this actually leads to such an even load distribution that if you look at it in one of our graphing tools, you cannot tell each server from one server from the other because all the lines are coincident upon each other. This is almost 100% the holy grail of load balancing. So now, of course, billions of DNS requests come in from AOL people. They all get served across the DNS farms. And keep in mind, this is a cluster. There are many other clusters like it. This one is mine. I wonder if people caught that reference. Some did. So that then does the DNS server implementation. Of course, the same technique is also applied to modulo-like stateful things like TCP across web caching. And so basically now we can scale any of these in arbitrary dimensions that we require. Now, streaming, that was caching. Let's take a look at streaming. Streaming, a simplified view consists of 3 blocks. You have the unified storage, where basically you take all your, this is the repository for all your content. You have hundreds of gigabytes, terabytes, I don't even know how much, I don't even want to know how much, because storage is expensive, put into the unified storage complex. The unified storage complexes actually then split it out to the content distribution network, which comprises, for the purpose of this talk, of 2 pieces, the UltraVox and NullSoft video people. The NullSoft video people do things like clips and on-demand content. UltraVox does things like streaming. Shoutcast, for example, if you listen to almost any shoutcast, AOL radio, radio at Netscape, they're all coming from the UVox. So basically, the UVox is a set of protocols, set of hardware, and again, it's a full presentation if you want me to go into that. We'll just stick with UVox for now. So the data is put into whatever format, real, NullSoft, MP3, and it's put into the repository. The UltraVoxes, the bedrocks, pull it out from the unified storage complex, encode it in UltraVox, send it to the UltraVox servers. And then, of course, when you click on a web page or something or listen to Shoutcast, it goes to the nearest UltraVox using a magical technique called multi-TCP for now, and you're good to go. And I'll just put the NullSoft video up here because I wanted to say send it to Death Star, because that's the code name for one of our live content servers. So this is what the cluster looks like. This is a mini data center in Chicago where basically this is part of the optimization for time and optimization for bandwidth. You take this stuff and then you push it out to the edges where the major peering points are. And if you look back at the slides, you'll see Chicago is one of the major peering points. So you have ATDN, you have peers coming off these routers. Peers go off these routers. You have a router there. You have UltraVox, which at this point consists of specialized hardware which fetches content and then does a unicast replication split. I wonder if Dave Meyer is here. No, we're not going to use multicast for this. And NullSoft video, this is the Death Star complex. So for example, if you click on CNN and you want to see a video or a news clip, that is served off of the Death Star complexes. This over here, and we'll go into this in more detail, is the unified storage complex, which consists of some arrays. We'll go more into detail. The systems that push content into the arrays, there's fiber channel over IP replication across to the West Coast, and then you have the same information happening there. So basically they're synchronized over FCIP. So we have encoders on both coasts that dump data into the repository, and it's magically synced across to either coast. So this is what a unified storage complex looks like. So you have some magical method of getting data into the repository. The repository is then synced across to the other repositories. And when people like Death Star, people like Ultravox want content, somebody goes and joins, for example, and wants to watch a video clip, they go to the Death Star. The Death Star then does a web NFS load balanced request to one of these servers, whichever one's available, and then the closest one, and then you dump that clip over to the Death Star, and then the Death Star sends it out to the user. So what this means is that you have things like speeches and video clips, trailers that people want to see, that would, if we unicast split them from the data centers, would take up terabytes of bandwidth. Now we only send out 1 to 10 copies, and we replicate them 100, 200, 300,000 times at each edge. So this is a huge, huge gain, statistical multiplexing. Then, of course, there's things like live content, which is always painful to do no matter where you are. This has never been easy. So we have this thing called the Broadcast Operations Center. So a lot of live content is encoded in the BOC, and then you send it out to the unified complexes. And then within the unified complexes, we actually do some kind of multicast. This should make Dave slightly happy. And the multicast is only to act as a transport bus within the data center. It never leaves the cluster of hosts that it is connected to. For example, let's take a large news corporation. This is not CNN, by the way, just so the news corporation encodes their data, and they send it out in 2 or 3 bit rates, just using 2 here. And then we put it to the transmitters. Here we go. So this is a large news site. They encode their content, send it over the backbone into these live transmitters. These live transmitters collate and then send the data into the distributed streaming on the unified storage complexes, which are distributed around the backbone. And then, of course, those put it in the repository and then out to the end users. So this is what the BOC looks like. How are we doing on time, Susan? Oh, well, I'll hurry up. I know people are hungry. I'm hungry. So this is what the BOC looks like, and again, the problem with this is that the density of information is high enough that you really can't see anything, so you just have to go by what I say. A lot of these hosts do encoding. There's monitoring, so you monitor the video streams, you monitor the encoders, you put stuff into the unified storage complexes, and then you push it out from there. So this is basically the nerve centers, so to speak, of the AOL streaming complexes. So any questions? And before this sounds like a Oscar speech, I would really like to say this is a very large and very complex operation. No single person or even single group of people can do this. So some of these people are here. I would really like to thank them. Some of these are actually here. There's James Watson, Terry, raise your hands. These are some of the engineers that work on this and make this a reality. This is a major pain to operate, run, and design for. And there's a lot of hard work that goes into this. I'd like to give my thanks to these people. And yesterday, while actually most of us engineers were standing outside at the AOL party, the soiree, we were handing out those USB key thingies. Did everybody get the USB key thingies? And there are a group of people, like NANOG people, walked by, and I overheard some of them talk, and they're like, "Who are these people?" And one of the person in the group replied, "Oh, they must be the marketing guys." So for you guys, This is not sales and marketing. We were actually engineers doing the sales and marketing job yesterday. And I'll end with a final quote, which I promised the Amazon guys I would show. Questions? Avi?
What issues did you have with authentication? Sorry, what issues did you have with authentication when you started caching streams, streaming objects, with sites that are doing user authentication and things like that?
Yes, there are. I'm not going to go into that. It's extremely complicated. But yes, we had authentication issues. We have solved them. I'm not sure if I'm allowed to say, because I didn't go into that, what exactly we use. Because some of that is IP that we have surrounded by legal fences.
Okay,
that's part of the core company.
That seems like one of the tricky, complications.
Yes, I mean, actually, let me give you a little hint of some of the stuff. So when I was saying that there's all kinds of reverse natting and forward natting happening here in the IPT farm switches, are you familiar with the AOL concept of DAHA, which is the dynamically assigned host address? Okay, basically when you connect, you get two IP addresses. You get your IP address from the RAS when you dial up, and then when you connect to the AOL service and you authenticate, you also get another IP address inside the tunnel, which is known as the DAHA. And the problem with the DAHA is now that you're running the DAHA, the tunnel, into the IPT tunnels, which de-encapsulate the AOL protocols and then expose IP, and then they use the DAHA to do the authentication inside the complex. The problem with that is that the request came in from a RAS IP address. You're operating on the DAHA. Now you have to maintain a mapping between the RAS IP address and the DAHA. And that is some of the tricky IP property that is fenced around by legal issues. So unfortunately, I cannot go into that.
Spencer Dawkins, you were talking about using multicast within data centers.
Yes.
Is that like? I was just curious what kind of order of magnitude you were talking about on receivers for that.
So basically, it's very small, really. First,
Is this on? No. Yeah. The multicast itself within the data center is not that large of a magnitude, but what it does is saves us from having to replicate, thousands of unicast streams to all of the edges to replicate it. So it is very helpful.
Essentially, a multicast is a data bus, the data transport bus inside the thing. If you really want to know about multicast, I would suggest talking to the Amazon people who I believe run. Is Ed here? There's Ed. Ed runs probably one of the largest SCOM and G multicast networks in the world at this point, I would imagine. He would be a much better person to talk about this in more detail. Any other questions? Going, gone. Thank you.